Spin 1 over n. Hello everybody. This paper is about spin 1 over n. The title of the paper is Visualization of spin 1 divided by n through spinning light clocks. My name Tao. Here is the abstract. Spinning light clocks are employed to conduct the visualization of spin 1 over n. N is a positive integer. An object with spin 1 over n looks the same if it is turned around revolutions of an integer number of n. For a spinning light clock, the two mirrors rotate around a common point that is between them, and the common point is called the center. There are two types of spinning light clocks. One is A-type, the other B-type. For an A-type, the distances between the center and the two mirrors are same. For B-type, the distances are different. The general method to visualize spin 1 over n is provided, and specific examples are given to visualize spin half and spin 1 over 3. Here we introduce two basic concepts. One is spin 1 over n. The other is spinning light clock. What is spin 1 over n? The answer is that an object with spin 1 over n looks the same if it is round revolutions of an integer number of n. Here we have three examples. Example 1. Spin 1 means an object looks the same if it is round revolutions of an integer number of 1, such as 1, 2, 3, 4, 5. The next one 6, and so on. Example 2. Spin half means an object looks the same if it is round revolutions of an integer number of 2, such as 2, 4, 6, 8, 10. The next is 12, and so on. Example 3. Spin 1 over 3 means an object looks the same if it is round revolutions of an integer number of 3, such as 3, 6, 9, 12, 15. The next one is 18, and so on. What is spinning light clock? Here we show an example of A-type spinning light clock. The two mirrors rotate around a common point. It is called center. The center is here, and the distances between the center and the two mirrors are same. The two mirrors move along a same circular trajectory. In this video, photon is marked by the green color disk, and the light trajectory, also the photon trajectory, marked by the blue line, and mirrors marked by the black color blocks. Okay, here we can see that this kind of pattern constructs a light clock, and we call it A-type spinning light clock. This video shows another kind of spinning light clock. It is called B-type spinning light clock. The two mirrors rotate around a common point. It is called center. The center is here. And the distances between the center and the two mirrors are not the same. They are different. One mirror moves along this circular trajectory, and the other mirror moves along the other circular trajectory. So here we can see that this kind of pattern constructs a light clock, and we call it B-type spinning light clock. In the next step, two examples of visualizations will be given. One is visualization of spin half, the other visualization of spin 1/3. Visualization of spin half. The first demonstration is by spinning light clock A-type. The second demonstration is by B-type. This is a visualization of a spin half through A-type spinning light clock. Initially, the photon here is at the bottom position with the blue mirror, and then the clock starts spins. Okay, here we can see we will first have half revolution here. Okay, half revolution. Next step, we will have one complete revolution. Spin, 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 spin here. One complete revolution. And next step, we will have 1.5 revolution. Spin, 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 spin. Okay, here 1.5 revolutions. And finally, we will have two complete revolutions. Spin, 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 spin. Over here, two complete revolutions. Okay, here we can see that after two complete revolutions, the photon and the blue mirror all go back to the bottom position. The light clock retraces itself after 2 complete revolutions. This is spin half. Here we show how to visualize spin half through B-type spinning light clock. Initially, the photon is here at the bottom position, and then the light clock starts spinning. Next step, we will have half revolution. Okay, here half. And the next step, we will have 1 complete revolution. Spin, spin, spin. Spin continued. Here we have 1 complete revolution. Next step, we will have 1.5. Spin continued. Spin, 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 spin. Alright, spin here. 1.5. Next step, we will have 2 complete revolution. Spin, spin, spin. Here is 2 complete revolution. Alright, after 2 complete revolutions, the photon and the blue mirror all go back to the bottom position. The light clock retraces itself after 2 complete revolutions. This is the spin half. Visualization of spin 1/3. The first demonstration is by A-type spinning light clock, and the second demonstration is by B-type spinning light clock. Here we show how to visualize spin 1/3 through A-type spinning light clock. Initially, the photon is here at the bottom mirror. Initially, photon is here at the bottom mirror, and the clock starts spinning. Next step, we will have a half revolution. Here is half revolution. Okay, we got half. Next step, we will have 1 complete revolution. Spin, spin, spin. Spin continues. Here we will have 1 complete revolution. Okay, 1 complete revolution. Next step, we will have 1.5 revolutions. Spin, 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 spin. Here is 1.5. Okay, 1.5. Next step, we will have 2 complete revolutions. Spin, 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 spin. Spin continued. Here we will have 2 complete revolutions. And next step, we will have 2.5 revolutions. Spin continued. Spin, 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 spin. Here is 2.5 revolutions. And finally, we will have 3 complete revolutions. In the next step, spin, spin, spin continued. Here we have 3 completed revolutions. Alright, after 3 completed revolutions, the photon and the blue mirror all go back to the bottom position. The light clock retraces itself after 3 complete revolutions. This is spin 1/3. This is to visualize spin 1/3 through B-type spinning light clock. Initially, the photon is here at the bottom position, and then the light clock starts spinning. Next step, we will have half revolutions. Half revolution in here. Okay, we got half. And in the next step, we will have one complete revolution. Here, we wait for the moment of 1. Okay, here we have one complete revolution. Next step, we will have 1.5 revolution. Spin, spin, spin continued. Here, we will have 1.5. Alright, 1.5 revolutions. Next step, we will have 2 complete revolutions. Spin, spin, spin continued. Here, we wait for the moment of 2. Okay, here we have 2 complete revolutions. Next step, we will have 2.5. Spin, spin, spin continued. Spin, spin. Here is 2.5 revolution. Next step, we will have 3 complete revolutions. Spin, 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 spin continued. Here we will have 3. Alright, we wait a moment. Alright, 3 complete revolution. We see that after 3 complete revolutions, the photon and the blue matter all go back to the bottom position. The light clock retraces itself after 3 complete revolutions. This is spin 1/3. Now we introduce the general method to visualize spin 1/n. Spin 1/n means that the object retraces itself after every nth revolution. A complete revolution corresponds to 360 degrees. Initially, the photon is at the bottom mirror of the spinning light clock, no matter it is A type or B type, and the bottom mirror is at the lowest point of the circular, and the clock is said to have a character of spin 1/n if the photon goes back to the bottom mirror after the clock makes every nth revolution. N revolutions means the clock rotates 360 times n degrees. Here, a concept named Haptic Number, denoted as P, is introduced. Haptic Number is a positive integer, and this number corresponds to the number of time intervals. One time interval is the amount of time corresponding to the half-take of the light clock, and it corresponds to the one-way situation in which the light ray leaves one mirror and reaches the other mirror, and the angle through which the spinning light clock spins in each step. In each step, the light ray leaves one mirror and reaches the other mirror. This angle is denoted as alpha, and it is determined as the following. Alpha equals 360 times n over 2p. The following proves that if and only if p and n are co-prime, the spin 1/n can be realized. First, if p and n are co-prime, then we know that the light clock retraces itself after every nth revolution. Second, if p and n are not co-prime, it means that n over p can be reduced to m over q. Equation 1 says that if p and n are not co-prime, n over p can be reduced to m over q. Here, m is smaller than n and q is smaller than p, and m and q are co-prime. So we have the equation 2 here. 360 times n over 2p equals 360 times m over 2q. From the above equation 2, we know that spin 1 over m happened to the light clock. That means that the clock retraces itself after every m's revolution, not n's revolution. That spin 1 over m, not spin 1 over n. Thank you.